I hope everyone is doing outstanding. I do miss seeing people in person, but the advantage of having an online class is that you can do it anytime. You can do external resources. You can use Chat GPT, and the onus is on you to grow and learn. Now, last week we talked a little bit about the difference between traditional computer science, traditional data analytics, and business or business intelligence. And it's hard because in business, you have to know a lot of things kind of well. In CS, you might only have to know a few things very well, like algorithms and sorting and why certain algorithms work better. But in terms of business, I don't know if it always matters. We used a car analogy last week, and it's a fair analogy, or another way to think about it is, as an engineer, it might be a big difference to know that a car can get 42 miles a gallon versus 44. What type of technologies were in the car to make it get that extra 2 miles a gallon. But from a practical standpoint, if you're spending $70,000 on a new vehicle, which is outrageous nowadays, that 2 miles a gallon might only equal a few $100s over a year. It just might not be worth that much time from a driver to figure out the difference between 2 miles a gallon. Okay. There are things you can spend your time on to make money and to improve your life. So this is one of those topics. This is vectorization. Vectorization is the bread and butter of machine learning. It is everything we do. It's everything we do. Now, you can spend your whole life just studying vectorization, and it's so important. There's all different types of math involved. There's specialized databases. There's a ton of things involved in vectorization. And I don't want to teach you those things. I want you to be able to know what vectorization is when you're in a meeting and people are talking about it. And I'll give you a great example. We're currently in the process of migrating EMR. So EMR is a electronic medical record. So we have these EMR systems where basically we keep patient data. So I got to close a couple of these out here because I got extra windows open from earlier. So we have all these different EMRs, and we have to merge them together to one big EMR. And it's applicable that a patient might be seen by different services. You go and you see your primary care doctor, but you break your leg and you go see an ortho doctor, an orthopedic specialist, or a dentist. It doesn't matter. Well, they might have two different systems. Those two different systems might not communicate with each other. So I enter my information as a doctor in one system, or your information in one system, and then you go to another doctor and he enters your information in another system. But now that we're going to one system, we have to figure out a way to merge all that data. And this is a very common, very, very common process. You buy a company out and you want to ingest their customers into your database. Salesforce bought Tableau. How do we see what customers were part of Salesforce and part of Tableau are now in one big data set? Mergers happen all the time. These things are very common. And I was in a meeting 3 days ago. I can actually look at my calendar. But today's Sunday, I think it was probably Thursday, about this very topic, vectorization. And we had 40, 50 people, and they're all IT, all analysts, all nerds, some managers. And they talked about vectorization, and I could tell instantly, probably 2/3 of people had no idea what they were talking about. Because they come from a background of traditional analytics, not machine learning. And vectorization is more of a machine learning idea. So that is the type of idea I want to instill in you, is what vectorization is, why it's important, and how we can use it. I don't want you to get into cosine similarities and all the math. I have I think I did code one cosine similarity kind of nerdy kind of demo. If you guys want to play with it, you're welcome to. It gives you the raw methods of doing things. Now, software does all this, but sometimes it's good to have a fundamental understanding of it. So that's why I did that. So we're just going to kind of cover chapter 5 today. It's not going to be a real long lecture. And then I haven't done the homework yet for this because I want to get all the book didactic material done. Then I want to get the homework done to you later. We already have that quote, so let's go. Okay, one thing that I didn't cover, and I think I should. It's important. Is a pickle. I'm Pickle Rick. So when we get data, we get it in, we work with it, we play with it, we save it. How do we save it? It should be a simple question. How do we save data? And in Python, there's about 20 different ways to save data. CSV. Now, they take comma separated values, but it's not always comma separated. I mean, I've done tilde separated, which is, you know, if you're Spanish, it's tilde. I don't know how else to say it. We do pipe, which is up, down, tab delimitated. But basically all that is we have a chunk of data separated by a delimiter. XML, Excel, these are all, you know, XML is not, but Excel is another method. Excel, some people love it, some people hate it, because Excel can kind of keep the formatting, but it can also mess up its formatting. It has compression, HDFS5, JSON, and SQL. Those are probably the most common ones. If I had a list in my job and in the real world, probably what you see the most of is probably CSV, probably Excel, and then either XML or JSON, maybe SQL. And when I say SQL, I mean either writing it to a database or saving it to an SQL file like an SQLite. So that's how we get data out. Now, those are probably all the worst methods we can use, but everyone uses them because, you know, VHS versus beta. Beta, I guess, is better, and I never had a beta player, but it's better, you know. Parquet is a method I use a lot. Your book talks about a pickle. Now, what makes these methods so different? What makes them so magical? And I'll tell you, one thing that makes them magical is it can save the formatting or save the data type. Let me get a little bit more particular on that. What do I mean by that? If you have a bunch of columns, okay, and one of them has a bunch of numbers in it, 5, 10, 8, just whole normal integer numbers, 12, 18, but for some reason it saves it as a string, and you're trying to do a join, you're trying to do some type of math operation and average, you can't. Because you can't average orange, green, pink, and lemon. You can't average those. They have to be numbers to do an average. Well, CSV and a couple of these other ones, SQL kind of supports data formats, don't support data structure types or data types. Pickle does. Okay, so that's one huge thing right there. So if I make a column with a bunch of numbers and I say, hey, these are numbers, Pickle and Parquet will basically both say, hey, these are numbers, let's save it as a number. If I go to another machine, I send it to somebody else, they open it, they automatically know that that is a number. Okay, so pickles are a very common method to export and import machine learning models, data frames, things like this. And I can't stress enough. For a lot of what I do, I use Parquets personally, but pickles work just as well. You know, yeah, it's Python specific, so it may not be readable by other languages. I just really wanted to hammer that home. Pickle is a very common data format for machine learning, and Parquet is a little bit more for big data. HDF5 is another one too for big data. Excel is capped at like 1 million or 1.5 million rows. CSV, you lose all types of formatting, but it's uncompressed and it's huge. So there's that. Data frames. Now, when we're dealing with NLP, I can take a chunk of NLP data, I can shove it into a variable, and I can process that variable, or I can put it in a data frame. Now, a data frame, what's data frame? Data frame's like Excel. I mean, I really don't know of a better way to ever explain it, but that's the way it was explained to me, and I guess it kind of stuck in my brain. But basically, it is just like, literally like an Excel format where you have rows and columns. But Richard, is unstructured data. Yeah, but I can throw unstructured data into a row, into a column. Hey, line 1, column, so row 1 would be, hey, the first sentence, second sentence, that's one way to do it. You put a whole paragraph, put whole books. If I look at Instagram and I'm looking at the pictures, or whatever, Twitter, it doesn't matter. I might have a user ID, and then I might have the picture associated with it. Not generally a blob, but you'll have a link to it. But you get the idea. User Richard Young, picture. User Richard Young 2, picture. And it's in some type of data frame. It's in some type of logical organization. Okay. There are advantages and disadvantages to using data frames. I generally use them. NLP, it's hit and miss. I think for bigger data sets and machine learning, you'll see data frames used almost exclusively. For a lot of demos, people will just throw into a variable. I put some pros and cons of each of them in here. I'm not even sure where I got this, but just be aware of that. That sometimes throwing things in a data frame is not always the best thing. If I just had to analyze, a book, maybe a few thousand lines or 300,000 characters, maybe I might just assign it to a variable. It was just one chunk of data. I would probably just throw it to a variable. If I was looking at 10 million Amazon reviews, I would throw it to a data frame. So just keep that in mind. We talked about regex a little bit before. Again, I just really want to stress regex. You don't need to know it. You don't need to be an expert in regex. You just need to kind of know what it is. You need to be able to Google resources. And, if I say, hey, let me give you a business proposal here, or a business idea. This is applicable. This is real life things. Hey, student number 2, we'll call you Todd. Hey, Todd, I have a data set here of all the car sales from the last year. So, hey, I run a car sales business. Okay. I run Fairway Chevrolet. And I'm getting all the car sales that we have from last year and all the customer comments and all this. I have all this data. First row is the customer name. The second row is the customer phone number, address, customer comments, everything else like that. Now I have this big data set. Now we're hiring this specialized company called Search Engine Magic. And they promise that, if we give them some data, that they can make our sales go through the roof. But I don't want to give them my customer information. So I'm going to rip off the customer name. I'm going to rip off the phone number, the address. We're going to keep maybe the zip code of the customer. That seems fair. But now in customer comments, I want to be able to verify that when I send my data set to, Great Magical SEO, I want to make sure there's no information like, this car was so great. I'm going to tell all my friends about it. Tom, at myspace.com. I want to rip off all websites. I just want to make sure in the comments that there's no telephone numbers. I'm never going to buy this from this dealership again. It's the worst dealership. If you have questions, text me, Richard at, area code 916-380-2941. I want to rip off that data. I want to just give them the raw kind of, the comments. So they can use those comments to kind of target SEO better on what people like. So you might have to go in regex in that column of comments and rip off any characters, any digits. You might have to look for social security numbers or addresses or zip codes and rip that stuff off before you send it to a third party. That's very, very common. Okay. Again, it's not something you're going to have to be an expert at. I mean, CS people know how to do regex really well. I know how to do regex. I do it against my will. But it is something that is very, very common. In my job, for example, I check all the time for social security numbers. We're not allowed to use social security numbers as identifiers. We get in a lot of trouble on a federal level. So anytime I send data anywhere, I have a little regex code. I just run it through all columns, make sure there's nothing that's like a social security number. Things like that. Another thing, too, I want to talk about is GPUs. I think the book has just a snippet on GPUs. I'm not really sure. GPUs are both a blessing and a curse in computers. We would not have modern computers. We would not have LLMs. We would not have chat GPTs without GPUs. Okay? GPUs are graphical processing units. And basically, they're video cards that were designed to play video games. Well, that's interesting. I have one here on my computer right now. So how does a video game processor, how does that make life so much nicer? Well, I can tell you. They're designed to do very simple matrix operations, addition, subtraction. They're meant to do it very, very fast. So they're very focused and they're very finite towards what they're supposed to do. So they're very fast, a lot of cores, super great. The problem is they can't do very much. They're very specialized. And you can't just take normal code and shove it to a GPU. It doesn't work that way. You have to have like CUDA, you have to have something specially designed, OpenGL, to process this data. Okay? So for most projects in this class or in general, we don't use GPUs. Now, once we move to machine learning, we use a lot of GPUs. Like I said, there's a lot of advantages both ways. One of the last supercomputers I designed, we specifically did not use GPUs because we're using certain specialized software that can never really be optimized for GPUs. GPUs tend to have not a lot of memory, so you have to move things in and out a lot. But GPUs can just terrorize CPUs. My GPU has, I don't know, that's a lot. Let's look. Yeah, so my current GPU sitting right next to me, I have 16,000 cores. Let's think about that. 16,000 little CPUs that can do math compared to my regular desktop computer that has 32 cores. It's just, you can't even compare the two. So let's dig into vectors. In vectors, one way to think about it is just a long string of numbers, a large collection of numbers. That stat quest, I'll post both of these videos, it's a little complex, but I love stat quest and a lot of their videos, so that's why I'm going to post this in the link for you. If you want to dive more into it at a data level, that's probably the video I'd recommend. If you want to dive into it as a CS person, that's Stanford. I guess that's right. They have a couple lectures on vectors. But in a nutshell, a vector is just a way to take words into numbers. Now, there's millions of different ways to do it. And there's millions of different thoughts on how to do this. Okay? But at the end of the day, when we say a vector, that's what I want you to think of, a long string of numbers. Okay? In our EMR system, and you kind of got to think about this for a second. If I have the word Richard Young, I was born in Las Vegas, Nevada, and I currently live in Las Vegas, Nevada, or Rick Young, which is a derivative of Richard, born in Las Vegas, current in Las Vegas, but I also have the word Richard Young, but born in New York and lives in Paris, France. You can just see, as a human, you can see that the first two are much closer. I mean, if I was just to take the alphabet and, I don't know, R is maybe the 20th letter, I is like the 15th letter, and I just add them all up. I do the same thing with the second one, do the same thing with the third one. These two numbers would be much closer than either of these two. So that's what a vector is. So that's how we do matching in a lot of ways. We use vectors to try to match things that aren't exact. We can use fuzzy logic and a lot of other things. But vectors allow for the quantification of similarity between words or text. Words with similar meaning tend to be closer together in the vector space. Okay? A lot of deep learning, a lot of deep fakes, a lot of GANs. We use vectors and we try to figure out a way to make these vectors similar to each other in order to make the images as close as possible. Most machine learning algorithms require numerical input. Vectors are a way to transform inherently non-numeric, symbolic nature of text into numbers. Also, we can do dimensional reduction. We haven't really talked about dimensional reduction. I'm assuming, that you guys know at least the basics of dimensional reduction, like PCA, T-sign, things like this. And we'll talk about it a little bit more next week, but dimensional reduction and the curse of dimensionality is basically when you have so many columns that it makes it hard to work with that data. That's kind of an oversimplification. PCA, principal component analysis, is a method where we can take big chunks of data, figure out what's important, and kind of reduce it. Say, hey, this is 70% important, this is 80% important. Let's remove the things that are 10% important, making our data set smaller. We can go into a couple of these other ones, but vectors are just super important for everything. I have this code that I provided, and I'm trying to think what I did with this one. Basically, I have 3 sentences, and I should have picked better sentences, but I want to convert them to vectors, okay? So we just did this real simple code, and you can kind of see. So here's what document number 1, or sentence number 1. So this is what it would look like as a vector. You visualize it now. This is what sentence number 2 would look like as a vector. Sentence number 3 is a vector. Okay. You know, there's multiple ways of doing this. We're getting rid of like word order. We're getting rid of syntax. You know, those n-grams. We're getting rid of all that, and we're basically just kind of. I'm just looking at one of my vectors, not right. We're just trying to convert it to numbers so we can run it through a machine learning processor. Bag of words vector. I have this code. I'll share it with you. We can grow on this. The super important idea. How do you take something that is not numbers and convert it to numbers? Here's another method. Again, I have code for this. A little bit more modern method, where you use the document frequency. Again, the document, you know, we tend to think of a document as a whole corpus. A document can be a sentence, it can be a paragraph, it can be from a start of a word to a period, it can be one row of text. When we think of a document, we don't necessarily think of a Word document. We can define how big our document is. Okay. And after the midterm, this is why I want you to get bogged down in the details. Basically, after the midterm, we're going to use transformers, and we're going to use Hugging Face. And literally, this is how easy Hugging Face has made this. And I've said this before in, I don't know, first or second class. I think in the future, you're going to see, maybe not Hugging Face, but a lot of these models integrated into applications. Okay, what do I mean by that? I mean, hey, if you see something on the web, either in Hugging Face or whatever comes in 10 years, say, hey, I want to use this model in Tableau. I want to use this model in Power BI. I want to use this in Excel. There's going to be a lot more interconnectedness. Okay, so this is just a transformer from Hugging Face, and I just said, hey, what do I do? I'm trying to read it here real quick. I did simple tokenizer on those same 3 sentences. Actually, one of the sentences was a little different because I had to add more words to it. But you get these results. And what this does, did I give you a breakdown of the results? I didn't. This tells you that sentence 1 is the same as sentence 1. Duh. This tells you that sentence 2 is the same as sentence 2, and sentence 3 is the same as sentence 3. Okay? Just so you know how to read this when you run the code, which I'll probably go over in more detail. Sentence 1 is related to sentence 2 at kind of a 91%. That's not really the best method to imagine that, but that's their similarity. Okay? Sentence 1 is similar to sentence 3 at 84%. So I can say, if I want to summarize or I want to do some type of cool stuff, that sentence 1 and 2 are more similar. Their vectors are closer. If I look at this one, sentence 2, which is, I wish I could scroll up on this. The sentences are like, sorry, let me find them real quick here. Machine learning, blah, blah, blah. So these are the 3 sentences I ran through here. And then I want to see the similarities. And again, this is so easy with transformers or with Hugging Face. Now I can say, hey, that sentence number 2 is more similar to sentence number 1. And again, sentence number 3 is closer to sentence number 2. So again, I have code demos for this, and this is where we'll spend a lot of time after the midterm. Okay? working with Hugging Face, learning what it can really do. Because again, I feel that, you know, in the future, you're going to see these models be incorporating into a lot more programs. Now, one thing maybe your book talked about, and I just didn't see it, is vector databases. So we talked about traditional databases very briefly. This is not a database class. We're not database experts. But databases generally store normalized data, chunks of data. If you have an address, you know, 123 Elm Street, I don't know, Freddy Krueger Way, whatever, we can store it either as a big chunk of data like that. We can break up the address, 123 Elm. We can put the street on a different column. There's different ways to break up or to normalize database data, okay? Well, that doesn't really work for vectors. Vectors don't do really well in databases. They just don't. How do you index a bunch of random numbers? If I was to give you a bunch of words and say, hey, I need you to index this, well, you could alphabetize it and say, hey, the letter A's are in this row, the letter B's are in this row, the letter C's are in this. You could alphabetize it. If I gave you a list of millions of addresses with states, and I said, hey, I need an index. And all an index is, it's just a way that says, hey, if you're looking for Nevada, go to row 400. An index is, you know, like a table of contents in a book. Looking for chapter 3, it's on page 18. How do you do with that? How do you do that with a vector? It becomes very hard. So they made vector databases, and they're relatively new. Vector databases are designed specifically to store vector information. Okay, there's long strings of numbers. The two main ones, I guess this one is this, but it's this Facebook one and Pinecone. Pinecone is very common. You'll see that deployed a lot. But the things that make vector databases kind of different or special is indexing. They can index vectors. So if I'm looking for this vector, I need something very similar to it. I know that my vector database will have some type of index and say, hey, go search in this kind of area and you'll get close to it. They can scale, where not that normal databases can't, but with vectors, they don't do very well. They integrate with machine learning pipelines very well. Okay, so I just wanted to touch on that. Again, I don't think your book covered vector databases. They're becoming more popular. They're becoming much more popular, I'll say that. So, again, I know that's a real general kind of takeaway. What are we at? 30 minutes, which is super short for a lecture. But please maybe research vectors a little bit, look into vectors. This book goes a little bit more into detail than I want with vectors. I'm going to see if I can post some additional reading about vectors. But if you can really kind of wrap your head around what a vector is, why it's important, you know, how we can take words, pictures, anything, and convert them into numbers, and then how we can compare those numbers, it becomes life-changing in terms of machine learning and what we can do. There's a project, and this is not 100% accurate, but we have Google Deep Variant, okay? So how do we take DNA, real quick, Deep Variant. How do we take DNA, which is basically 4 characters, and how do we look for variants on it? Well, what we can do with Deep Variant is we can kind of convert that, it's not, again, not 100% accurate. We can take A, C, T, and G, the DNA, and convert it to CMYK, the colors, or RGB, and just throw one out. And then we can kind of look for pictures of variants. We can look for similarities. We can look for vectors. Now that we have A, T, C, and G, the DNA code, into numbers, we can do amazing things with it. And that's why this Deep Variant was so amazing when it came out. Nothing else was like this. There's really no way to find variants in genes very quickly and with the amount of accuracy as Deep Variant. I mean, this thing won all types of awards. I don't know if they list them here. But just because it took A, T, C, and G and converted them into numbers and then basically ran a machine learning algorithm kind of on it. So that is why these vectors are so important. That's why it's so important to find ways in your head to convert colors, words, into vectors, into numbers that machines can do things with. Because remember, 80 to 90% of the world's unstructured data. So thank you again.